Extra highlighter. Welcome, everyone. Hey, thank you for joining me on page 366. We're going to terminate or culminate our interior angles of a circle theorem with a proof, because that is what we need to do when we are actually getting ready to use something. Please have the following vocabulary words, just maybe like on standby. We have talked about inscribed angle theorem from page 360. We have talked about, well, actually make the card interior angles of a circle theorem and have that one ready to go with, writing the definition on the back in page 366. We might need this one, triangle sum theorem, how the angles in a triangle add up to 180. We might need this one, the exterior angle theorem, where if you have a triangle, then the two remote interior angles will be equal to the measure of the exterior angle added when it's added together. Know what we even mean by the interior angle of a polygon, because as we are creating our relationship for the interior angles of a circle, that might be a case. Arc addition, there's definitely a potential for some arc addition to happen. I think I've seen it in the previous videos. Angle addition, if we're adding arcs, we're probably adding angles. Some other vocab that we've done, the definition of a central angle. Do you even remember what a central angle is? Were you paying attention when it was made as a vocabulary word and put on the word wall? It was a Mathia workspace that you were working on. Do you know about intercepted arc? The intercepted arc that is created when chords in a circle are generated. Do you know about the definition of supplementary angles? I mean, honestly, it's been another vocab word that has been around for forever, because the supplementary angles that we're forming might actually be like a linear pair, or they might be the interior angles of a circle. And then our pal, substitution. Whenever we need to do a replacement, substitution saves the day. We're finishing off 366, which is a formal proof or semi-formal proof of the interior angles of a circle. And there was a relationship that was discovered in the previous videos. If you have this interior point and it's created by, crossing chords, then the angles created by those chords will be half of the sum of the intercepted arcs added together, some arc addition. So we're going to actually go ahead and just prove that this holds true for any two chords that intersect inside a circle. And then I think I'm going to, again, use the information, the given that's here, highlight the given in yellow or a color. And I don't have my customary pink. I guess I'll use orange. Highlight the prove in orange. We're going to start with yellow given, and we're going to wind up with prove orange. Now, what we did in the previous pages, and flip back as you see them, right, is that we actually made some lists of things that we knew. So, for example, we know that chord EK and GH intersect at point F. And therefore, we can say that, KFH, right? KFH is this angle that we're trying to focus on. Let's start with that one. Let's draw. Let's do what we draw auxiliary line. So it's mentioned as a highlight right here. It's the dotted line here. Let's draw the auxiliary line EH. And when you do that, you end up creating something that we highlighted yellow in the previous examples. It creates this lovely little triangle right here. Okay, so it's kind of like in our proof. We're just going to go ahead and just launch into it. So we're drawing an auxiliary line EH to create triangle EHF. Okay, there it is. Now, in that creation of that triangle, this is also going to allow us to establish that HEK is going to be half of the intercepted arc. So we should say that, okay? That means then by the intercepted arc, or by that theorem, where did it go? One of these is our vocabulary, the inscribed angle theorem. So I'm actually going to say this. So by the inscribed, there's weird spelling there, angle theorem, two things actually end up happening. Let's highlight both of them. So I'm going to highlight this angle. That's HEF. And I'm going to highlight this other angle, let's use, I guess, orange for this one. Highlight this angle. Those two angle arc relationships are described by this. That means, by the inscribed angle theorem, the measure of angle HEF is half of arc HK. Green to green? Okay. HK. Also, EHF, the measure of angle EHF, so that's orange, is going to be half the measure of arc EG. That's by the inscribed angle theorem. Okay? So now what we can do is we can say I'm going to add together HEF, so I'm going to add green with, let's see, EHF with FHE. So that'll bring up the exterior angle theorem. Okay, by the exterior angle theorem, finding it out of my pile here, by the exterior angle theorem, if you have remote interior angles, right here, you have remote interior angles on a triangle, then when you add them together, it'll be the same as the exterior angle. And in this problem, HFK is an exterior angle. So I'm going to say, by the exterior angle theorem, then I'm going to say what that is. All right, what that is, I'm going to add up the measure of angle HFK, so this one, is going to equal the measure of angle FHE. I use this notation EHF. I'll use the same lettering, EHF. Same thing as what I just said, but in reverse order. And then plus the green, plus the measure of angle HEF. So I can therefore say that if I add these two together, I get the remote, I add these two remote interior angles together, I get the exterior angle that's on the outside, the one we want to focus on. Now, with our pal, find him. We've used it so many times. With our pal substitution, if I have two of these, it's like I added these two together. So because I have these two added together, I can just substitute what they're equal to. So with a straight substitution, probably time to switch up the color. By substitution, ooh, let's bring in some highlight. All right, bring in some highlight. I highlighted EHF orange. And I highlighted HEF green. So by substitution, green will go to green and orange will go to orange. The thing that's not highlighted sticks around. The measure of angle HFK equals 1/2 the measure of EG plus 1/2 the measure of HK. That's a K, right? I had to adjust. So we're almost done, right? If you go back and look up at the thing we must prove, it says we have to have the 1/2 separated out in front of everything. It's like the reverse of distribution. In fact, it's called factoring, and it's an algebra property, and I'm going to just jump into what you need to say. So therefore, the measure of angle HFK, the thing we're supposed to prove, is equal to 1/2 of the measure of arc EG plus the measure of arc HK. And that is what we needed to prove. We're done. Please make sure that you have created your note card for, find it. Not you. The interior angles of a circle theorem. Because now we have this relationship that will help us solve problems, and it should work, it will work for every single relationship that's out there when we have a point created by two crossing chords inside a circle. And we want to know their angle measures. Thank you for watching this video. Activity 3, the exterior angles. We did interior. Activity 3 with exterior angles is next on page 367. See you in that video. Keep learning, keep exploring. Stick around.